Good morning, everyone. This is Shanmukaraju, roll number P24CI0205, external PhD student from Department of Civil Engineering, IIT Jodhpur. I am going to present a research paper titled as MoBA, that is Mixture of Block Attention for Long Context LLM. This research paper is authored by the researchers from Moonshoot AI, Tsinghua University, and Zhejiang University. The main goal of this paper is to make transformers efficiently process extremely long inputs all the way up to 1 million tokens. Basically, large language models are now used in tasks involving long sequences like books, video transcripts, logs, and agents that need memory. But there is a big problem. Attention is in the order of quadratic, meaning it becomes too slow and too expensive as the input grows. There are sparse attention methods, but they are either too rigid, too task specific, or breaking the original transformer design. So we need something that scales efficiently, preserves accuracy, and stays within the transformer framework. Hence, the core objective of this MOBA is that it should work within standard transformers, reduce the compute and memory, learn which tokens that matters, scales up to 1 million tokens and beyond, and support efficient inference. That is the main goal. Now, what is MoBA? MoBA stands for Mixture of Block Attention. The key idea is very simple. Instead of attending to the whole sequence, MoBA breaks the sequence into blocks. Therefore, for each query token, it always attends to its local block and it selects only the top k most relevant blocks that select. Hence, the selection is learned using a gating mechanism similar to the mixture of exports. So basically, this flowchart shows the MOBA architecture. As I already mentioned, the entire key and value, the input sequence is broken into the number of blocks and it is processed. And this router is basically called as the gating mechanism. Block partitioning. Now, the first step is to divide the sequence into equal token blocks. Each block is a continuous span of tokens. This gives the structure to the attention. So the model does not need to look at every token, and finer the segmentation helps the model learn better. This we will see in the later part. Once the sequence is divided into blocks, MOBA applies a mixture of expert style routing mechanism. For each query token, it pulls the keys inside each blocks. It computes the similarity between query and each block. It sorts the block by its score and it picks only the top k highest ranked blocks. The current block is always included, and importantly, causal masking ensures no future token are accessed. Basically, the masking prevents including the future block, and always the current block is included. And due to the mixture of expert mechanism, it already picks only the top k blocks. So that is the main idea. Now let us see the MOBA algorithm in a big picture. As usual in the normal transformer architecture, there are queries, keys, and values. Here, the keys and values are divided into blocks, and the pooling of the keys is done inside each blocks, and block scores are computed for each query, and causal masking is applied to prevent the inclusion of the future blocks, and top k past blocks are selected and current one is included, and entire output is merged. The attention output is merged. Basically, MoBA is a general, rather, it is not only an attention architecture. It can simulate the full attention for all K blocks as well. And it can simulate a sliding window mechanism. It can simulate streaming attention mechanism. It can simulate the sync attention mechanism and any other many research variants. So it is not just a sparse framework, and it can be used for many other attention patterns. One of the biggest strength of MoBA is its efficiency. It works with flash attention kernels. Since only a few blocks are attended, computation becomes block sparse. The key value cache is also partitions. Instead of attending to all tokens, we only need to attend top K blocks plus local block leads to major speed at long context lengths. This can be seen in the image, the image which is extracted from the research paper. If we see the dark blue line which depicts the MOBA efficiency, it is very efficient when in comparison with the flash attention mechanism. Or now comes to the testing phase. The authors actually tested MOBA on model sizes from 568 million parameters to the 2.1 billion parameter models. Actually, in the 8K context, that is 8K token context, MOBA matches full attention even at 95% sparsity. Hence, MOBA keeps small context performance intact in parallel with the are unequal with the equivalent with the full attention. But while scaling it with the 32K context, MOBA maintains the full attention score degrades. Basically, we can see in case of 8K, it is 2.622, and in case of 32K, basically, in case of full attention, it is only 1.464. So basically, in case of larger token context, the full attention degrades, and MOBA maintains low trailing token loss. So which can be used for book reading, reasoning across section, and very long output tasks. Basically, in the ablation study, we have to note that the sparsity is kept constant, but the block sizes are changed. From this figure, we can easily understand that the coarser blocks means lower learning performance, but the fine-grained blocks means it results in the better learning performance. So we can easily understand that even though it is the even though it is in case of sparsity also, by doing the blocks fine graining, we can get the better learning performance. Now, authors have tried this hybrid training strategy also. That means they have trained MOBA, and then on top of that they have trained full attention as well, and vice versa. Which means they have first tried full attention, and then on top of that they have trained with MOBA, which resulted in basically due to the full attention, the accuracy kept intact, and due to the MOBA kind of architecture, it resulted in speed and efficiency. So that is the outcome of this hybrid training strategy. Now, next step is Llama. This MOBA has been tested in Llama 8 billion model with 1 million, as I already mentioned, with 1 million context tokens. So here in the stable, we can easily see that the MOBA performance matches with full attention while scaling it with 128K context tokens. Here, we can easily see that in case of MOBA, the score is basically 0.7818. In case of full attention, it is 0.7849, which means there is a very, very minor variation in comparison with the full attention for MOBA, while scaling it up to the 1 million parameters, 1 million tokens, that to a large LLM, that is Llama, with 8 billion parameters. One of the toughest tasks is needle in a haystack benchmark. A small string is hidden inside a massive context, sometimes hundreds of thousands of tokens long. MOBA is able to retrieve it correctly up to 1 million tokens. So MOBA wins in speed and accuracy. Hence, the key contribution of this paper, we can say that MOBA, a new scalable attention mechanism that is fully compatible with the standard transformers, works at extremely long contact lengths efficiently without compromising in the accuracy. Now comes to the limitation. We can say it is a limitation, but it is rather, I would say, it is a kind of a requirement. If always efficient strategies require efficient implementation. Similar way, here MOBA also requires efficient and careful implementation. And here the gating or this routing adds overhead. Yeah, it is there, we have to accept that. And the performance depends block size. Basically, as we saw, coarser block results in rather, I would say that the finer blocks resulted in better learning performance. And we can extend this in future with the learnable block segmentation and multimodal or video tokens, and we can test it beyond 1 million. Now it is being tested up to 1 million tokens. We can scale up it beyond 1 million, and we can study how how MOBA performs. To conclude, MOBA is a general sparse attention framework which is efficient, flexible, and accurate. It scaled successfully up to 1 million long sequences, keeps transformer compatibility, and future ready for long context LLMs. Thank you so much.